Okay, so after talking about unusual distributions, we're going to branch up into uniform distributions. Unusual distributions are sort of made-up examples that sort of allow us to see mathematically an easier way to how to calculate these probabilities. It turns out with a lot of distributions, there's not an easy formula that'll get the job done. But we do start with uniform, which is a specific type of distribution out there. So what makes a uniform uniform? Well, it's a continuous distribution where the likelihood of a particular event is evenly distributed amongst all the probabilities. In other words, there's an even probability that anything could possibly happen. Rolling a die is one example. So the likelihood that a 1 would show up, or a 2 or a 3, um, those are uniform probabilities. Graphically, we draw them in the shape of a rectangle. And the formula is to calculate the mean, and this is the variance here. So if I want standard deviation, then I want to take the square root of this. And then just in the formula's sake, A and B represent the endpoints of the distribution. So when we're talking about the area then, so we got to kind of remind ourselves we're talking about a rectangle. So how does one find the area of a rectangle? And that's just length times width. So let's look at an example and then kind of figure out how to set up a uniform distribution just based off this idea of a rectangle. It's got an area of 1 underneath the curve. What would that look like? So here we've got the Citrus Sugar Company packed sugars in bags labeled 5 pounds. However, packaging isn't perfect, and in reality, when you weigh them, you actually get 4.98 pounds on average, and the range is somewhere is 0.2 from low to high. Okay, so we got to think about what would that represent? Well, we start with drawing a rectangle, and we label the center of our rectangle as 4.98. A range of 0.12 means that if you go from the low end to the high end, you're looking at 0.12 there, which means technically it's 0.6 above and 0.6 below. So it looks about like that. Now, the only thing we're missing in our rectangle then is the height of it. Keep in mind the area of this particular rectangle has to be 1. And since we know the range, we can fill in the height as 1 divided by 0.12. Now, I realize we could type that in a calculator and get it at a number, but I want you to understand that it's 1 divided by the range to figure out the height of the uniform distribution. And now that we've got this constructed, we can actually look at answering questions about the probability of an event occurring. So let's say I would like to know what percent of the time, given these parameters, would I expect to see something bigger than 4.97? Well, I know the height of the rectangle. Now we need to know the width or length of that. And I could just take out a calculator. And let's see, we know the 5.04. So let me clear that off. 5.04 is on the high end, minus the 4.97. And so that gives me a length of 0.07. So when I put that in the formula of length times width, 0.07 times 1 divided by 0.12, I get a area of 0.5833, which means about 58% of the time I would expect to see something bigger than 4.97. Okay, let's keep going with this. What about, I'd like to know what percent of the time do I get something between 4.93 and 5.03? Well, again, I know the height of the rectangle, so I just need to know the length here. So we'll type that in, 5.03 minus the 4.93, and that'll give us a width of 0.1. So type that in our, put that in our formula. So 0.1 times the height of 1 divided by 0.12, and that gives us a probability of 0.833. So about 83% of the time, I would expect to see something between 4.93 and 5.03. All right, let's change it up and look at a different example. Look at the time it takes for students to drive to school. So we're going to suggest that it's evenly distributed with a minimum of 5 minutes and a range of 35. So the smallest time it takes to travel to school is 5 minutes, and the range, meaning as high minus low, is 35. So if I think about that for a second, what would the largest time be? It takes 35, the difference being 35, so that would mean 35 plus 5 would be 40. And the height of our rectangle is 1 divided by the range. So our distribution looks like this. And then I can use our rectangle here to calculate the area underneath the curve. So what's the probability that it would take a student less than 20 minutes to drive to school? Well, 20 minutes is the top part of the rectangle. So 20 minus 5 would be 15. So 15 times 1 over 35 gives us that probability there of 0.4286. So I would, about 42% of the time, it would take less than 20 minutes to get there. What about mean and standard deviation? Just remind us of the formulas we saw at the start of this little video. So the mean of a uniform distribution is add up the endpoints, divide by 2, and the standard deviation, the variance, so we're looking at standard deviation squared. So the variance is this, and find standard deviation, square root the variance. So filling in our numbers, I get the mean is, let's see, endpoints would be 5 and 40, so that's 45 divided by 2 is 22.5. So generally speaking, I expect it to be about 22 minutes and 30 seconds to get to school. And then define the standard deviation. Plug that in the variance formula. So I get 1.02, 1083, and then if I just take the square root of that, that gives me a standard deviation of about 10 minutes. So there you go.